Awesome. All right, so let's get this show on the road. Um, so, hi, friends from the Zen community. Welcome to my talk titled Safety and Security Design Patterns for Automotive and IoT Software Compositions. This is actually the second time I've had the good fortune to be invited to do a keynote here. Quite proud of that. So, I'm Robin Randhawa and I work for ARM. Right, so super quick intro. This is like the summary of my professional career. My background is in electronics engineering. I got the software bug when I was in uni. Did a startup with friends in India in Pune called Cogito. The slogan was Cogito ergo sum, which is a wordplay on Rene Descartes' Cogito ergo sum, which is I think therefore I am. This was that code, therefore I am. We added support in GCC, bin utils, and those kernels for a processor from ARC and also a processor from a company called Cradle, which is a chip multiprocessor. Did that for 6 years, was fun. Moved on to MIPS at Cambridge as a part of the Linux kernel group, support for their first hardware multi-threading processor. Lots of cool stuff over there. MIPS decided to make a couple of bad moves, ended up in ARM. I kept telling myself I'll leave next year, and I've been around for 14 years, so now I'm kind of like institutionalized, I suppose, is the word. Just a second. Right. So, I had the good fortune of being a part of the first open source group in ARM. That was one of my roles. That was platforms. I then did operating system BARPOF stuff. There's a team that was responsible for big. LITTLE enablement, energy aware scheduling in the Linux kernel, landing it in Android frameworks. If you have a Pixel phone, it's running my code. And now I'm the architect for the Automotive and IoT systems team. Okay. Right. So I put in a lot of words in my kind of like presentation outline, but there was a reason. There's some points I want to make over here, and then those points then help me kind of articulate the agenda. So Zen is a key component of an open source software stack that we do in the Automotive and IoT team at ARM. And people ask me, oh, if it's going into automotive and IoT, why are you using open source stuff? In my last keynote, I gave that topic a lot of attention, so I would urge you to kind of look at that for the details. But simply put, we were looking for a vibrant community and a good feature matrix, and Zen gives us all of that. Why do we need something like Zen? Because virtualization in the context of automotive and IoT is obviously very important, and we want to use Zen as a vehicle, no pun intended, to disseminate best practices. So the kind of like the approach I've taken here is that I want to talk about how we are using Zen right now, and as I'm talking about that, explain what are the popular software compositions that we see in the industry, and some that we don't, but which we are meaning to kind of engineer, and then talk about stuff that's on the horizon, right? And kind of like that bit is more about trying to seed thinking more than anything else, but I'll come to that. So how did it all begin? We basically got into this place at ARM where vehicle autonomy control became hugely important. And the reason ARM decided to do this is everyone else who's in the business of doing kind of like automotive is doing the same thing. As in tier one players, OEM suppliers, those kind of people, right? Everyone wants to come up with a nice, functionally safe, certifiably safe way of doing vehicle autonomy control. And this graphic is just like a hugely simplified kind of example of what a typical implementation for vehicle autonomy control looks like, right? Um, and it's got like a pipeline of software that consumes data coming from multiple sensors at the left end, so LiDAR, radar, camera, sonar, those kind of things. And it kind of like fuses all of that using industry standard algorithms and produces like this nice standardized representation of the environment of the car, immediate external environment. Then it tries to kind of classify what it sees over there into people, road signs, tracks, whatever. And then it tries to kind of use all of that information to calculate a trajectory, and then it turns that calculation into commands for, velocity control, steering, that kind of stuff. Now that's all cool, but where does Zen come in? Zen comes in because we need a hypervisor to help with freedom from interference of each of these kind of stages of the pipeline, right? So yeah, we have this is basically what we're trying to do in our stack. So what is it that we do with Zen, right? And I thought of different ways of kind of expressing this, and this is what I came up with. It may not be ideal and it may be a little redundant, but I think it carries the message well. So we've got 3 swim lanes really. There's one that's focusing on foundational work. There's another one that's focusing on actually putting Zen to work, like, functions. And then there's this extension of Zen, like, taking it to the next level to support safety and security, right? So I want to kind of like explain these 3 tracks. So yeah, the graphic on the right is a tongue-in-cheek way to show that, there's arm that's represented by the hand, and it's got this yin-yang symbol, right? So good versus evil, but I'm not implying anything. I prefer to think that Zen is the good one and KVM is the bad one, but my loyalties are clear. So yeah, the point here is that inside ARM, a lot of the architectural decisions for virtualization architecture were made on the basis of type 2 hypervisors, right? Like KVM in particular. And while that is fine, most of the kind of learnings and the design of the architecture should kind of naturally become applicable for type 1 hypervisors as well. But we always felt that, there's going to be areas where we need type 1 hypervisors to be in focus, right? So that's one of the areas where we're kind of working, right? This is a mindshare building thing inside ARM. So you go to the architects and you tell them, okay, yes, have you considered a type 1 hypervisor, right? And this is what the world looks like then. So that's one thing that we're constantly doing. This is an interesting one. The graphic on the right side is a poor attempt at showing a level playing field. And what I'm trying to say here is that because KVM was the focus of attention for architectural insights, insights that dictate the evolution of the ARM architecture, and because KVM is what it is, right? It's a part of the Linux kernel pretty much. It automatically benefited from all of the goodness that Linux gets, right? And Linux gets a lot of goodness at ARM, understandably so. So things like support for new relevant architecture extensions and errata fix-ups. And Zen has tended to build up a very large technical gap in this regard. So this is another area that we are constantly trying to kind of improve. My good friend and colleague Bertrand Marquis, who I know is on the call, is somebody who immediately saw the value of taking this problem on, and we made a lot of progress. This is a continuing track. So when I say parity, I mean parity with KVM Linux in that regard. Okay. So then there's the composability improvements, right? So yes, you've got a type 1 hypervisor, and yes, there's a really nice established way of disseminating the Linux kernel, right? And our partners know how to take that dissemination and compose software with it. But how can we make that easy for people in the automotive and IoT space using Zen? And that's where we came up with, okay, let's build on Yocto and come up with well-designed recipes that allow you to mix in Zen easily. So that's another ongoing kind of activity. And over time, we kind of like want to extend this to stuff outside of Zen, which is also going to be part of the system and will be important. Okay, and then there's the quality improvements angle, right? So over time, we have invested in improved CI for building all of the stuff that we do in our full stack, including Zen. I'm very fond of static analysis as a general mechanism, and I want to try and, for robustness of software. So we use Coverity in ARM, but unfortunately not for Zen just yet. So that's on my plate as one of the things I want to socialize and make happen. It would be really cool if the output from our team is suitably targeted with Coverity as well, right? And there's the Zen test framework aspects as well. So we've looked at it. There have been some early discussions, although not comprehensive ones, on what we can do to improve the story there. Okay, so now here's where the interesting stuff happens, right? So this is where the design patterns come in. Like I said in the outline of the presentation, this is what I wanted to tell people, right? So yeah, this is obviously not going to be a surprise to you guys, but the use of Zen as a static partitioning hypervisor is increasingly popular For that matter, not just Zen, type 1 hypervisors, but used as a static partitioning mechanism. What do I mean by static partitioning? I mean, like, there is a affinity between virtual machines and physical resources that's set once and actually doesn't change for most of the lifetime of that run of the product, right? So what is the hypervisor doing there then? It's actually acting as an isolation mechanism, and for the large part, it's not intervening unless someone does something nasty, right? So what we want to do is we use AutoWare as our reference kind of workload for vehicle autonomy. We want to slice up the pipeline, and we want to run each pipeline in a separate Zen virtual machine, and then look at industry standard communication middleware for comms between them. Okay, so that's basically one way of promoting freedom from interference, right? The kind of like the type 1 proprietary RTOSs, that's bread and butter for them as well, right? So we want to kind of like, our perception is that this wasn't the intended primary usage model with Zen, right? So we're kind of taking it in new spaces, and I know Stefano's done a lot of work over here with the DOM zero less design pattern. That's an area that we are kind of using and socializing as well. We haven't really done a lot of comprehensive work with that just yet. That's because some of our other related parallel tracks of work were also in flight, but it's all coming together now. Okay. So this is another interesting one, right? So in the vehicle autonomy control space, the people have started seeing this now, right? You can't kind of focus on the really complex kind of top level algorithms for vehicle autonomy. I mean, that's hard enough. And then at the same time, you also don't want engineers to break their heads on dealing with the nuances of the BSP underneath, right? Remember that we're talking some fairly esoteric stuff over here: GPUs, machine learning accelerators, NPUs, those kind of things. So the vision that a lot of companies, including ARM, are having, and we're just at the start of that journey right now, is that how far can you take abstractions like VertIO, like industry standard abstractions, and abstract all of the underlying hardware complexity of it, including accelerators, such that basically the currency for expressing these autonomy workloads becomes like this virtual machine that relies on VertIO underneath, right? And all of the hardware kind of complexities are encapsulated using VertIO, and in the Zen case, possibly a DOM0, which becomes the BSP domain, right? So there's a lot of work we're doing in this space to try and understand how Zen can be used over here, how VertIO and containerization can be used. And this is becoming a really big deal. A lot of companies are now kind of getting up and saying that, look, this needs to stop. Of course, there's the trade-off, right? Oh, you're adding more abstraction into the mix. What does it mean for latency? What does it mean for throughput? All good questions, right? The hope is that if we can find the pain points in a pattern like this, we can then quantify those pain points and express them to system architects, etc., and see how much can be resolved. But it's worth doing. The fact that people are talking about it is quite enlightening, right? People are now like, oh my God, we need to solve this. Right? Okay. Now, I've just given this a funky name, and Bertrand, don't get upset because I literally just thought of this last night. Okay. So I'm calling it DOM-X, but this is another area where we are focusing a lot. The idea is that I've kind of like put in over here DOM0, right, as the safety island client in this graphic over here. Assume you can see the pointer. Yeah, right. So, but what this really is about is that in highly safety sensitive applications, you kind of want to separate the primary compute, right, the stuff that runs your vehicle autonomy control pipeline algorithms, from this external entity which is implemented in hardware and software to be of very high quality, right? What I mean from a safety standpoint, right? And what is its role? Its role is actually to deploy work on the primary compute. Its role is to monitor it. Its role is to kind of control it. And control also means things like updates and stuff like that, right? So this entity by the side is the industry uses different names for it, but I think what everyone wants to say is like a safety island in that sense. So we want to try and we already have kind of systems that are being designed to service this pattern, but in the context of Zen, we want to see whether, hey, can you have a DOM0 less thing on the primary compute and yet have some degree of control of that from this DOM-X? And how do you implement a Zen monitor application that can run under an RTOS? What about like a Zen controller traditionally the function of DOM0, right? Can you express that as an RTOS app in a nice compatible way? Those kind of things. So the aspiration is to try and do this with DOM0 less, although we are conscious that today that presents some problems. Okay, and so this is now the futures thing, right? So I've kind of shown the two design patterns I wanted to talk about. One is the isolation design pattern, and the other one is this kind of external monitor, this DOM-Ext thing, right? An external domain that can control Zen. And by the way, this is not the stuff that I said previously is not new. It has come up in previous discussions. We're just reaching a point where we can bring it all together and do something concrete with that. Oh, and then for the future, right? So discussions on this have only just begun. There's a bunch of ARM architectural extensions that came up in the v8.x context and moving onwards, which are safety and security centric, and we are now beginning the discussion inside ARM to understand how that can be leveraged for Zen. So it's PAC, BTI, MT, Morello, and MPAM, and in 30 minutes, I can't do that justice, but I'll zip through all of those to give you a bit of a flavor. Please treat this as a kind of like a conversation starter, okay? So yeah, pointer authentication. Basically, this is a mitigation against return-oriented programming attacks, right? So where people will mess around with the stack and doctor the return addresses, try to find code sequences that they can stitch together by careful manipulation of the program counter through the stack, and then do really scary things, right? So what happens over here is that basically what ARM has said is that, pointers will be encrypted using a key, right, fundamentally. And before you use the pointer, you will verify on that pointer whether its integrity using that key. If it is valid, then you'll go ahead and process that pointer, like dereference it, whatever. If not, that's a fault, basically. You get an exception, right? So there are instructions added for creating, like adding a PAC, this pointer authentication code, into higher order bits of a virtual address. And then verifying it and removing the pointer authentication code and a framework for keying, right? So it's primarily intended for making user space more robust. And I feel that at the minimum, we'll need to kind of like have Zen be able to enable access to this functionality for vCPUs themselves, so that the guest kernel can then go ahead and do the right thing. But it's going to be like, like we're at the start of that journey. So like, I think at the minimum we'll have to do that. And then there's the question of, can Zen itself, for its own reference management, its own pointer management, also use PAC, right? Please look at the kind of URLs for more information. So BTI, this is also interesting, branch target identification. Again, it's another kind of vector for which this protects against, right? So this is jump-oriented programming. The idea is that you mess around with branches, like indirect branches that use a register containing an address to be the target of a branch. People would very craftily take over the stack and then manipulate some of these registers and then force execution to kind of use a string of these gadgets, right, that they wanted to use. So what branch target identification does is, for pages where there are these targets of indirect registers, we'll have a special instruction called a landing pad that we'll have to put at those sites. And then for the page containing these instructions, you have a kind of like a identifier, right? You have a GPI flag in the page table descriptor. And once you do that, from that point onwards, once you tell the CPU, I'm going to be, all indirect branches must use these landing pad instructions. The CPU will then check to see whether the target of your indirect branch contains a landing pad instruction or not. If it does, cool. If it doesn't, it's a fault. So again, this functionality needs to be exposed to user space. So that's one aspect where Zen will probably have to do something. But then there's also the similar question: can Zen be used? Can BTI be used for Zen itself? Memory tagging is basically, this is like the memory safety mitigation, right? Memory unsafety mitigation. So it's like use after free, buffer overflow, underrun. I probably don't need to tell this audience how prevalent that style of problem is. Like 70% of most known issues and most major software compositions have this problem. So what does this do? It's very interesting. Every 16-byte physical address granule, right, is given a 4-bit tag, right? So once you have that tag, you then have the ability to kind of get the CPU for every virtual address reference, right, to use this tag, which is inserted into free higher order bits in that virtual address, right? Every time a reference is made using that virtual address, that tag, which is embedded in the higher order bits, is compared with the tag of the physical address that that virtual address decomposes to after translation, right? If there's a mismatch, that's a fault. Right? So there are instructions that allow you to kind of generate these tag values, set them for a block of memory, zero the memory while setting the tag, etc., etc. So again, it's for user space, and again, the minimum functionality will be just exposure to the guest. But then, what does that mean for Zen itself? How can we use NT inside it? Can we use it to kind of come up with a nice way of making Zen's own use of references more rationally from a safety standpoint, security standpoint? So you see, there's a theme over here with all of these features. Okay, so then this is interesting. Morello, and I think someone's made a reference to Cherry already. Yeah, so ARM has been working with the University of Cambridge, and we've kind of taken the ARM v80 architecture and added extensions to it, which are inspired by what the University of Cambridge has done with Cherry. In a nutshell, this is about capabilities. Capabilities is a concept that the microkernel ecosystem has been using for decades. The idea is that you have like an unforgeable token that represents a capability for accessing any resource. You may not access that resource directly unless you have that token in your possession, right? So the architectural definition of a capability is like a 128-bit word with one additional bit for validity, right? And there's lots of really useful documentation available for this. But simply put, it's like a pointer with a lot of extra metadata, right? Such as what are the permissions of the capability? What permissions do you need to have to access that capability? What are the bounds of access? You can limit the bounds. So in a nutshell, the cool thing is that people take the architectural capability concept, right, from a instruction set architecture point of view, but then they layer like a kind of abstraction, an abstract capability model on top of that for things like I want to make sure that accesses to the text section or the code on the BSS or the data section needs to go via capability. Stack accesses need to go via capability. Program counter references need to happen by, using a capability. Really, the sky's the limit. Of course, there are trade-offs, and what the FreeBSD project, along with Cambridge University, has shown is that you can do like this pure capability design where everything, including the kernel and the user land, understands how to use capabilities as a medium of kind of access, right? And it gives you some pretty bulletproof security. Now, I want to explore the kind of the notion of playing with virtual machines using the concept of this capability, right? Can we? This is not new. Folks have done this for the Hafnium kind of hypervisor at Google. It's public knowledge. There's a Cherry OS project that has also done it, like a pervasive use of capabilities for the kernel or for the hypervisor itself, not just for user space programs, right? So I want to kind of look at this and see what does it mean for a type 1 hypervisor. Now, we have a lot to look at and get inspired from already, but what does it mean for Zen? And can we do something about it in the Zen context, right? I think this is probably be something that either us or somebody in the ecosystem will have to do, or will have to do. Right? So again, for more details, have a look at the URL. Oh yeah, and then there's MPAM, right? So memory system resource partitioning and monitoring. This is another architectural extension, and fundamentally, it's about having a shared resource. And if you have a shared resource, and if you have some kind of a utilization semantic associated with that resource, and if you have the ability to partition that utilization or performance semantic, then associate that partition with a software construct, what you basically get is a nice way of shared resource control, right? And that makes, in the static partitioning example I showed you, the design pattern I showed you earlier, it's really useful to be able to say, I have this virtual machine that needs X% of the cache, or it needs Y% of memory bandwidth, or it's also permitted, as per the MPAM architecture, to extend this to buses, interconnects, fabric, that kind of stuff in implementation specific ways. So I think what would be really cool, we're a bit far away from a silicon implementation that can actually be used in anger to see what the possibilities are, but there's enough information available, enough modeling information available to start thinking about what does this mean for Zen, right? So some of the things I could think of, okay, how do you express shared shareability from a resource standpoint, right? Like of this sort. I don't mean shareability and cacheability from our architecture standpoint, for those of you who know this, but I mean generally there's a memory system resource that's shareable. How do I express it and tell Zen about it, right? How do I express performance attributes that can be the basis of partitioning? Would it make sense to have like a uniform scale for, like for resource performance partitioning, right? Could that uniform scale be used for dividing up that those partitions among different virtual machines, right? And then there's this concept of a part ID, right, which is MPAM's notion of the identifier associated with a shared resource partition. What would that mean from a Zen standpoint? Would Zen need some specific way to access resource control? For Linux, there are tools. There's this rest control thing. Right? What does it mean for Zen? Those kind of questions is what I want to look at over there. Again, please look at the URL for details. So that's the whirlwind tour of Zen at ARM. The goal was to tell you about the design patterns. I think I've covered that. And then the goal was to tell you about what we do at ARM with it, with Zen. And then tell you in terms of the ARM architectural extensions where we want to go next. So I've made this on either which ways. Please ask me questions. If I can't answer those questions here, we can have those questions offline. Just reach out to me. I'm specifically very interested in thoughts around the safety and security themed ARM architecture extensions and what people think about the technical problem of incorporating them in Zen, the political problem, if you like, of political is too strong a word, but you know what I mean, right? Like, what is the cost actually of landing this support? A lot of these probably will ruffle existing intent in the code, right? Kind of re-architect the existing code to allow assimilation of these features, those kind of things. Yeah, so right, and I'm just going to quickly go through the questions. Okay, George, I had a notional understanding that Coverity is being used. What wasn't clear to me was whether whether Coverity for Zen is being used for the ARM architecture, because I understand there's an architecture specific facet to this, right? So, Artem, it's good to know that you're running it internally on the ARM code base. What would be cool is if you could either share reports or if we can turn this into a community thing, right?
There is an ARM. There's an open source Zen on ARM separate sub-project that gets used once in a while.
Is that internal or?
No, that's on Coverity's public site.
Oh, super. Okay.
We've got two Zen projects there, one called Zen and one called Zen on ARM, I think.
Okay, cool. I had no idea. I will follow that up because that just might be a way to kind of do what I was trying to get done inside ARM. We'll see. Thank you for letting me know. Julian, hi Julian. Okay, good to know that even EPAM is doing something there. Is SPAC an implementation of the Cherry architecture? Not specifically. I think it's got a similar theme, but it's different. As in, Cherry is more encompassing than just signing references, right? Yeah. Cherry is Morello is correct. Now really looking forward to the Morello slide. Okay. I hope I didn't disappoint. Cherry is the open source one. Morello is ARM's implementation. That is correct. Hongyan Xia. I have seen that name on some papers. I assume it's the same gentleman. Hi. Jose Martins, you talked a lot about new ARM hardware features. You didn't mention the new CC architecture in realms. Can you comment on how hypervisor architectures might be modified to take advantage of this? Very good question. And my flower petal diagram of interesting architecture extensions to target for Zen actually had like a bucket petal called V9. I took it out. I took it out because, and this is just down to me, I myself have not had an opportunity to kind of soak in the CCA and realms to an extent where I would be comfortable making any articulation internal or external, right? So your point is moot. I think there is ample scope for overlaps there. right? So one of the kind of like one of the big deals with V9 is like this concept of a blind hypervisor. You might see it in, I'm sure it's discussed publicly, where you don't want the hypervisor to kind of peek into what it's running. And that's an area where I was wondering, what does it mean for a Type 1 hypervisor? Could there be something for Zen that we want to do over there? Would it be something that we would look at as the automotive and IoT team? Right? That's a good question. But yeah, so I'm sorry, I don't have. Yes, I did mention CC. I did not mention CC and RIMS. Fair point.